Hello and welcome to a short video. My name is Andy Schweitzer. This video is on just a very brief overview of how to name ionic compounds. A little brief background as far as ionic compounds go. Ionic compounds are a series of cations and anions, so this thing would form what I often refer to as a bulk crystal. Bulk crystal is a bunch of cations and a bunch of anions that are fitting between them, and vice versa. It just simply forms what I refer to as a bulk crystal. And I'll just do a few more rows here just to get you the general idea. Oh, that should have been a negative. And the inherent nature of a bulk crystal affects a lot of how an ionic compound actually sort of reacts. And I'm going to just draw an outline of this showing that it's also in 3 dimensions. Now, we can split this bulk crystal right in half, and it could easily still be the same crystal on one side versus on the other side, the same substance. So there is no specific number of individuals that are in here. It's just a huge, like I say, bulk cations, bulk anions, and they're piled up. In order to give the name of this substance, what scientists have done is said, okay, we can't really tell how many there are, so we're just going to tell the simplest ratio that occurs in the crystal. And this simplest ratio is referred to as an empirical formula. At this point, it should be somewhat intuitive as to why we would call this crystal, for example, NaCl, which is a simplest ratio of atoms. Right? Empirical formula by definition means simplest ratio of atoms versus, let's say, Na2Cl2. This would be something that would not exist. It exists, but you'd be insinuating that these 4 perhaps have a unique relationship as opposed to all the other guys, and that just isn't the case. Right? So every single name for an ionic compound is going to be an empirical name, or I should say every formula is an empirical formula. So 2 things we're going to cover on this PowerPoint is, 1, how to write the names of these guys, and then also how to do the formulas and how you go back and forth between these 2 things. Okay. First thing I'm going to do will be the formula, and I'll clip a clean slide here, and we'll just try a couple examples here. The simplest one here would easily just be NaCl. Okay. For this crystal, we all know this is being sodium chloride, common table salt, although any ionic compound could be considered salt. This is table salt. What is the ratio between cations and anions? Well, it turns out there's 1 sodium for 1 chlorine, as opposed to, let's say, AlCl3. In this case, there's 1 cation for every 3 anions. Or let's say we have magnesium nitrate, NO3, 2. In this case, we have a cation here, and we have a polyatomic anion. This is a covalently bound anion, but I call it a polyatomic family. It stays very tightly bound within itself. It has a negative charge, so it acts as an anion. All right, so how do we come up with these formulas? They're not coming in the same ratios. How do we know which ratios these are? Well, it turns out that the cation is a cation because the sodium atom itself had 1 valence electron, and eventually it would give its electron to the chloride, producing a sodium cation and a chloride anion. For this purpose, because whatever electrons are lost or gained, then this overall charge should still be 0. All right. With that in mind, I'll simply give a few little rules here. for writing ionic formulas. First rule is we always write the cation first. Okay, just so everyone's on the same page. And second one, my charges, which are resulted of a oxidation and a reduction reaction combined, should always be balanced. The charge should balance to 0. Okay. Now, let's try a couple examples here. We have sodium, which will form a +1 cation, and chloride, which forms a -1 ion. The way I approach this is I'd say, okay, well, the charges will balance to 0, so how many +1 cations it would take to balance off the chloride? And the answer is one of these and one of these. Therefore, my formula is just simply NaCl. Okay. This guy, again, the formula is already completed, so if I had an aluminum cation and I had a chloride cation, anion, how do I go about getting this formula? Well, I go to my ion charts, or if you don't know them, check the periodic table or different resources that you have, and you found this guy is a +3 charge, and you should also be able to explain why it forms a +3 charge. And chloride, which is a -1 charge. How many of these -1 chlorides will take to balance out electrically the +3 charge? And that is, I need 3 of them. Hence, this is why this formula prevails. 3 -1s and 1 +3 balance out neutrally. All right, here, this is an interesting example where it shows the use of parentheses. This is a +2 charge. This is a -1 charge. So I need 2 of these entire anions in order to balance electrically the +2 charge. And again, that is why this is how this particular formula unit exists. 2 negatives, 1 positive, balance out to 0. 2 or 3 more examples, and we will proceed to the naming. All right, so let's just say I want to do calcium and hydroxide. Okay, this is a -1, this is a +2. How many hydroxide do I need in order to balance out the charge of the calcium? All right, it simply would be 2 of them, so it's calcium, parentheses, it's a family, so I have to have the family in the parentheses. The next one here we have, let's see, aluminum, which is a +3 charge, and let's say sulfide, which is a -2. This one could be perceived as being a bit harder. What do we need here in order to balance this? Well, there is a little shortcut rule, which is called the crisscross rule, which shows you how many you need. If you take this 2, bring it down here, and then take that 3 and you bring it down here, this will give you the option that will allow you to neutralize it. 2 times 3 is a -6. 3 times 2 is a +6. So my formula is Al2S3. Does that always work? Well, it worked above here. The +2 came down here, and the 1 came over here, and it's just invisible. Where this shortcut rule would not work would be, for example, here. Calcium, which is a +2, sulfide, which is a -2. And you say, okay, well, in this case, if I want to use my little crisscross rule, then the 2 would come here, and the 2 would come here, and I'd end up with Ca2S2. This is a violation. It's not an empirical formula. Even though it balances 0, this would not exist for an ionic compound. There is no, like I said in the previous slide, that would insinuate that you have a cluster of 4 ions, which just isn't the case. Every single ionic compound has to exist as a, as an ionic formula, or sorry, as an empirical formula. So if you get the situation where they're the same number, you would reduce it down. Or you can think of it as, how many -2s do I need to balance off the +2? 1. One of these and one of these balances to 0. So my formula would be CaS. From this PowerPoint, or this little video here, we've now shown how to set up an ionic formula, and how to use parentheses, and a brief introduction to this little crisscross rule. Now, as far as the names are considered, okay, how do you give this thing a name? Every single chemical has a formula, every single chemical is going to have a name which should uniquely identify that particular formula. So, for ionic compounds, it is quite simple. We are going to give the name of the cation and the name of the anion. And that's it. What's unique about this chemical situation is it never gives quantities. It doesn't, okay? So for example, AlCl3, however tempting it is to say, indicate there's 3 chlorines here, we can't. This is just simply going to be aluminum chloride. Okay. Let's bounce back to the previous slide. We'll give the names of all these guys that we've kind of written. This guy is calcium and hydroxide. That's all we simply do. Calcium hydroxide. It is the user of this name responsibility to flip it back to a formula and figure out the charges and crisscross it. This guy is just simply going to be aluminum sulfide. Okay. This is going to be just simply calcium sulfide. There is one unique situation where if we have multiple options for a charge, for example, we could have CuCl2 versus CuCl. 2 different chemicals. In fact, they're very different looking. This guy is bright lime green and this guy is sky blue. So both of them, if you give them your names, would be copper chloride. This guy would be copper chloride. Although they are 2 different substances, they're going to distribute the same name, and we just can't have that. So again, we don't give quantities for these guys. We give names. This guy is a -1 charge, and this guy is a +2 charge. Again, 2 -1s required to balance off 1 +2. Here we have a -1 charge, but this guy is only a +1. That's all that was required. So the big difference between these 2 chemicals is the charge. And we want to indicate this charge in the name. We only do this if there's multiple options. Parentheses, 2. Again, that 2 is not referring to a quantity at all, and students will quite often get mixed up with that 2 being 2 chlorines. It's not. It's referring to the charge here. This guy is going to be simply parentheses 1. Common metals that have multiple charges would be copper +1 or +2, iron +2 and +3. This would encompass probably 90% of our examples. We do also have tin and lead, which have both the same charge of +2 and +4. This would be 99% of the examples that I might give or see. So be aware of these guys here. At this point, you have the naming processes and you have the formula writing skills as well. You should, at this point, be able to take a name and flip it to a formula. So, for example, if I give the name, let's say, lithium phosphate, you should be able to convert this to a formula. You say, okay, well, lithium is a +1 charge, phosphate, PO4-3. Keep your ion sheets nearby if you need them. Check out the formulas. How many of these does it take to balance out this one big -3? I need 3 of them. You could use the crisscross rule if you'd like. Li3PO4. Make sure you use parentheses only around families if you need multiples of them. Another example here would be, let's say, NH4 parentheses SO4 2. So I got to give a name to this guy. Again, quantities do not matter. I have two, this is ammonium, two of them, and one sulfate. I'm just simply going to call it ammonium sulfate. This is just a basic preview. This should be followed up with a significant number of practice questions out of your workbook. Give them a try. Come see me if you have any questions.